Hello students, welcome to our physics lesson. We are continuing with the applications of Fermat's principle, and basically we are going to tackle proving the law of refraction using Fermat's principle. And now here we are going to consider a ray of light passing through two media, maybe from air to glass. We can use what we call this shape of a glass. Can be a glass block, and then we're going to consider a ray of light passing through this, incident on the glass, such that when this ray reaches the glass, it will be refracted. Remember, this is our normal line. So when this ray hits the glass, it will be refracted along here towards the normal. After being refracted, suppose this was the original source of light, maybe from point O and then to point A, being incident at an angle of incidence I and refracted at an angle of refraction R. Now if I complete this, suppose the distance from this point to this point is maybe L. This is my distance L, and also the distance from here up to here is X. Can make it distance X. So I can also determine this distance from this point up to this one. So it means it will be L minus X. So this is L minus X. Maybe if I call this point B. So we need to determine the optical path, the path taken by light to move from this point up to this point. So our optical path. Now before that, suppose this is from here up to here. Maybe you can say it is height H2. Can make it height H2. The distance from here up to here. And also we can make the distance. Let me complete this. From here up to here, I can make it distance H1. Height H1, such that now my optical path, L, optical path maybe L. I can make it capital D is equal to, now we shall get the refractive index from point O. Refractive index, of course, this is medium 1, which is air. I can make it N1 as its refractive index. Then this is the different medium, N2. So optical path is given by refractive index times the path length. So this is N1 times the path length from O to A plus distance. Of course, when the ray reaches glass, our refractive index is N2, then times the path length from A to B. Now we need to determine OA and AB. So our OA will be, so when you look at this triangle, this right angle triangle, of course using Pythagoras theorem, this distance from O, from this very point where the ray starts, from this point to this, it will be, here we shall have root of H1 squared plus this distance. Of course, this distance is the same as this, and we say it will be distance X. So it will be X squared. So this will be N1 into root of H1 squared plus X squared plus N2 times our, this is OA. Then our, from here to here, AB, it will be given by maybe you can leave this because we want to determine OA. So our AB will be, if you consider this right angle triangle, using Pythagoras theorem, of course this will be the root of this distance L minus X squared plus the root of this distance, which is, we said it will be H2 squared So our optical path, which is D, it will be N1 times OA, which is root of H1 squared plus X squared, then plus N2. Our AB is root L minus X squared, then plus X squared. Now from Fermat's principle, you know that if you take the derivative of the optical path, that is dd, we are differentiating the optical path with respect to x. It is always a 0 because we need to determine the time taken by a ray of light, and we are considering the minimum time. So we are going to differentiate this with respect to x. So our dd dx will be, I can put here a half. Of course, a root of a number is just to mean that number is forwarded to a half. So this is n1 into h1 squared plus x squared power half, then plus n2 times L minus x squared plus h2 squared. The whole of this is powered to a half. Now here we have not yet differentiated. That means this one is still d. So we are now differentiating this function. So our dd dx. So I'm dropping the power. This is a half n1. Maintaining this h1 squared plus x squared, and I reduce the power by 1, which is negative a half. Then differentiate what is inside, we shall get 2x. Then here plus, we are differentiating this, so I'm dropping the power first. A half into, I'm reducing the power by 1. After maintaining this, this is L minus x squared plus h2 squared. This is power negative a half. Then differentiating this with respect to x. When you reach here, of course, we shall drop the power first, which is a 2. Then you maintain what is inside, which is L minus x. After maintaining it, we reduce the power by 1 to remain 1 here. 2 minus 1 is 1. Then we differentiate what is inside here with respect to x. Of course, when you differentiate this with respect to x, it will be negative 1. The derivative of this with respect to x is a 0 because it's now a constant. So our dd dx will be, so when you look at these two, it is cancelling with this. And when I drop this one down, I will remain with x over, there is n1 here, the root of h1 squared plus x squared. Then here plus, this 2 is going with this. Then up here we are remaining with n2 times, we have L minus x. I'm dropping this function, so I'll remain with L minus x squared plus h2 squared, but under a root. So now we still have a negative here, so there is negative. So this is a negative one. So even if we take away this, this will be a negative. So when you equate this, when you put here a 0 from this expression, it means this one is going to be equal to that. So we shall have n1x over root of h1 squared plus x squared is n2 in the L minus x over the root of L minus x squared plus h2 squared. h2 squared. Now when you look at this diagram, x divided by h1 squared plus x squared under root. Of course we have our x here. When you consider this angle, this triangle, this one is equal to this, so this is the same as x. So when you get this over this, that one is a sine, opposite over hypotenuse. So this one is the same as x over this is sine I. Sine I. So this will be n1 sine I. And then looking at this triangle here, L minus x, it is the opposite of r. Then this expression, it is the hypotenuse of this triangle. So opposite over hypotenuse, of course that one is a sine. So this is n2 sine r. And you know that in most cases, the refractive index of air, which is n1, it is always 1. So when you make it 1, you will find that you will have our n2, which is sine I over sine r. And majorly this is the law of refraction. So when you reach here, it means we have proved the law of refraction using Fermat's principle. So that has been our lesson. Thank you for watching.